So we've looked at different elements of graphing, different horizontal and vertical asymptotes, but what about putting it all together? So today we're going to just go back again. I just want to hit this practice one. There's two practice ones here, but I want to do this one real quick. Domains are all reals except -1 and 3. Vertical asymptotes, well, let's check this first. We may be able to factor this, let's see, 9, I bet it's 9 and 1, x minus 9, x plus 1, over 3 times x plus 1, x minus 3. So you can see that your x plus 1 is going to be a whole at x equal to -1, and 1 vertical asymptote at x equal to 3. Just a quick reminder, x plus 1 equals 0, x equals -1 is how you would find that. All right, so with those canceled out, you're going to get x minus 9 over 3 times x minus 3. So we are going to have a vertical asymptote at x equal to 3. The horizontal asymptote, we can just go ahead and look at this quick. Take the limit, x approaches infinity, of x squared minus 8x minus 9. And that's going to be 3x squared. X minus 3x is negative 2 times 3 is 6x. Minus 3 times 3 is minus 9. When we take the limit as x goes to infinity, you're going to have 1x squared over 3x squared, and that's going to be equal to 1/3. So the horizontal asymptote, the y value, will be equal to 1/3. So now that we can find vertical, horizontal, and wholes, how is that going to look on a graph? So before we do the graphing, I just wanted to do a couple of kind of fun things, a little extra to make you think. This is honors pre-calc. One of the goals is to push your thinking in application and abstract ways. This is called the CAN problem, and we do this as a lab normally. I'm cutting back on the online class. If you were to make the ultimate CAN, how would the dimensions look? So for any CAN, you have a circle on the bottom, pi r squared, and you have a height, h. All right? How would that height and radius work? We could take that volume, and I just made up a volume of 1,000 cubic centimeters. We could make that a real tall, thin tube with a very small radius and a very large height, or we could have a very short height and a very large radius. Okay? If those volumes were equal, okay, notice that the surface area is going to get pretty big. The surface area of this thin tube is going to get big. The squash tube is going to be very big too. Somewhere between r being huge and h being huge, we want to get this relationship between h and r. What ratio is h to r to get the maximum, I'm sorry, not maximum, minimum surface area? Okay, so you can employ a number of different ways. You might consider building a formula for surface area and a formula for volume, and see if you can figure out how to relate those. That's one extra problem. Another extra one is a group activity that we do where you're going to sketch f of x equal to 2x plus 3, 4x over 4x plus 5, and from that information find the domain, the vertical asymptotes, horizontal asymptotes, holes, y-intercepts. See if you can find that, and then eventually do that with just the variables A, B, C, and D. So first, just go ahead and try to put these in terms of 2, 3, 4, and 5, and then see if you can do them in terms of A, B, C, and D, and see if you find some pattern. So those are 2 extra things to do. I think you might find them interesting. You don't have to do them. All right, let's look at graphing. So they make a suggestion on graphing a rational function. They do it in spurts here. They do the domain, which would be find your vertical asymptotes, and that'll help you know where the asymptotes are. Find the zeros, set the numerator. So here you're setting denominator equals 0. Here you're setting the numerator equal to 0. Both of these are going to form what we call critical points. The critical points are the places on the number line where special things are going to happen. Either they're going to go through the x-axis, or they're going to be asymptotes, so it'll go to infinity, come up here, maybe they'll go up here. We don't know. But if you set the denominator equal to 0, or if you set the numerator equal to 0, you'll get those critical points. I'm just calling them A, B, and so on. Then, once you have critical points, so let's say these are my 4 critical points, then what I would do for sketching the graph is do a test value for each of these. I'm going to put a little star here. Test value for each of these intervals. Okay? And then once you have those test values, if it's negative, it's below. If it's positive, it's above. And if you know it goes through the x-axis or goes up to an asymptote, you can get a better idea of what that's going to be. So here's your testing for that. So we're going to do one, and they even include in that, they do x and y intercepts, great idea, end behavior, great idea. These numbers are pretty arbitrary, but if you find the vertical asymptotes and zeros, so the numerator equals 0 and the denominator equals 0, then you can set up that number line and establish in your graph vertical asymptotes and zeros. Then find x, y intercepts, which are the zeros on the x and y axis, and then do that line. I would just draw a number line and put those zeros in, A, B, C, D, or how many there are, and then look at the plus and minus. Maybe it's up here, maybe it's down here, maybe it's up here, okay? And then do your end behavior. For this one, the end behavior would be up here because it's plus, and it'd be up here because it's plus. So just look at this. Let's say we had an asymptote here, and these were zeros. Well, you can kind of tell that it's going to do something like this, and it's going to do something like maybe this. And those plus signs and minus signs are super helpful in sketching the graph. Obviously, the best way to graph is with a calculator. But if you do the vertical, horizontal, vertical asymptote, and the zeros, check your intercepts, make your test line, pluses and minuses, and look at your end behavior, you should be able to sketch that graph pretty well. So let's do an easy one. Okay, here's one. We'll start off. We get a vertical asymptote, x equal to -2. There are no holes because nothing cancels out. The horizontal asymptote will be y equal to, if you go plus 0 times x, it's going to be 0 over 1, which is 0. Okay, we'll look for x-intercepts. We set the y equal to 0. And there is nothing, if you set y equal to 0, there won't be any x-intercepts. Y-intercept, you put x equal to 0, and that's just going to be 4 over 2, or 2. Okay? And with the number line, we have a vertical asymptote at -2, and therefore we have 2 test intervals. I'm going to put one at x equal to -4, which is going to be y equal to 4 over -4 plus 2, which is 4 over -2, which is -2. So this is going to be negative down here. A vertical asymptote there. And then I'm going to check out a positive value. Greater than this, let's let x equal to 0. So 4 over 0 plus 2 is going to be 2. That's plus. So my guess is, since the horizontal asymptote is 0, a vertical asymptote at -2, so let's do it this way. Here's a graph. 0, and I'm just going to call this -2. It's negative down here and positive up here. I would guess that this is going to be what my graph looks like. Notice my vertical asymptote at -2, horizontal asymptote at 0. There are no x-intercepts. There is one y-intercept at 0, 2. So I guess I have to raise this up a little bit here. It's got to go through the 2. There you go. That's a graph. And all of these, you're going to do the same thing. Vertical, horizontal asymptote, x, y intercepts. Make your line wherever the x-intercepts or the zeros and the vertical asymptotes are. You'll break that into regions, do your test intervals, and look at your end behavior, and you should be good to go. And that is graphing. You can try these, and some of them are more challenging than others, but I think they're interesting. And please take a look at this number 21. This is one of the puzzles, the things that I did earlier. That's it for graphing rational function.